the long-term stability of equation. And let's really start focusing on the really simple equation du dt equal to lambda times u. So here, let's do not assume that lambda is a real number. Let's assume lambda is a complex number, right? It could be I, it could be I minus 1, it could be anything. So let me first ask the basic differential equation question without any numerical method. Is this equation stable or not in the long term? Yes? Well, if lambda is a real value, you are right. It depends on if lambda is positive or negative. If lambda is positive, the solution explodes exponentially, right? If lambda is negative, it converges to 0 exponentially. But how about if lambda is a complex number? I mean, when we look at a complex number, we are usually drawing on a complex plane, right? The x-axis is the real of lambda, the y-axis is the imaginary of lambda. In which region of this complex plane would this differential equation, if we solve it exactly, be stable? Is the unit circle? Actually, no, because the unit circle actually contains a little bit of a positive real values, right? And the equation wouldn't be stable if you are real and positive. So it is not the unit circle.
To the left of the imaginary axis.
To the left of the imaginary axis is the right answer, because the solution, if you look at the solution is u equal to some constant times e to the lambda t, right? And if lambda is a complex number, you can split e to the lambda t into the product of two parts. One part is e to the real part of lambda t, which determines the magnitude of the solution. The other part is e to the imaginary part of lambda times t, which determines the oscillation, right? How fast does it oscillate? It's the real part that determines if it's stable or not. It determines the magnitude, right? So basically, whether the solution is stable or not only determines on the real part of lambda. And we know that for negative real part, the solution is stable. So let me just shade the stable region of the analytical solution, right? It's over here. Okay, so entire left half of the imaginary plane is the stability region of the analytical differential equation. So that's the stability region. And we want to extend the idea into numerical discretization, and we want to figure out if we apply, for example, forward Euler, can we recover this stability region? And if not, how well can we approximate the stability region of the real differential equation of the exact solution? So let's take forward Euler as an example. Okay, so forward Euler, we have u of k plus 1 minus u of k divided by delta t equal to lambda u. That's our forward Euler, right? Instead of we are solving the differential equation, we are solving this equation. And then the iteration becomes u of k plus 1 is going to be equal to uk plus lambda delta t times uk. Or if I can combine these two terms, that would be 1 plus lambda delta t times uk. Okay. So from this equation, we can start to figure out the stability region of forward Euler. Now, if you look at this equation, can somebody tell me at what condition do we need to satisfy for the forward Euler iteration, which actually depends on delta t and depends on lambda, to be stable in the long term? By long term, I mean if you apply this formula again and again and again for infinite many times, the solution wouldn't go to infinity. What condition do I need to satisfy?